Okay, hi everyone, and thanks for coming today. So today is actually more of a discussion session. So previously, with a few people at NeurIPS, like Shuchen is here today as well, and there's Joseph Campbell and Marcus Hiller, who are quite amazing people. Actually thought of an idea while at NeurIPS that basically uses a form of memory in order to help learning. Okay, because current neural networks don't really have this sense of storing an external memory for reference. And that may be, this is my hypothesis, that may be the reason why it takes so long for the neural network to learn something. So I've been thinking about it, like how do humans learn so fast? Like how can we learn how to extrapolate between different things? And actually, I feel like memory plays a huge role. So this sort of discussion is not complete yet, okay, but it's more or less like flesh out in more detail now. There's 38 slides. So I hope to take about an hour or so to cover this. And yeah, let's see where this goes. So the aim of this is basically to seek some biological, neuroscience, psychological insights, especially into as to how the human brain works, and try to use this kind of concepts to model it into current AI. And the aim is not to replicate the brain faithfully. The aim is to make AI learn faster and learn more like a human in terms of generalizing, which is currently its weakest point right now. So firstly, let's just take a look at this video. Okay, let me just show you this video on a separate. Let me just share my screen again. So yeah, so this video is quite cool. So this is about the star tracing task that Henry Molaison had to do.
One thing we didn't discuss about HM was a task they had him engage in. In this task, neural psychologist Brenda Milner, who was working with HM, had him perform a mirror tracing task like this one. HM was to trace within 2 lines of the star while viewing it only through a mirror, which was the reverse image. So if his hand moved one way, the hand in the mirror moved the other. They asked HM to perform this task up to 10 times each day for 3 days. They counted the errors each time he went outside of the lines. What's interesting is that HM's drawings improved, even though he couldn't recall having done this task before. Now you're looking at the times that I tried it, and I'll be honest, this task was really hard to do. So what does this tell us about the brain? HM didn't remember engaging in this task, but he visibly improved. Well, it turns out that he couldn't form new explicit long-term memories due to damage to his hippocampus and surrounding areas. But he could learn new skills, as was demonstrated by his performance on this task.
Okay, so yeah, that was the star tracing task, which is basically the task whereby HM needed to take us like from a star grid, start from one point, go through look through the mirror, and then follow this outline of the star. Any point that he exited the boundaries between the 2 lines is considered as one error. So in this cartoon chart here, you can see that this is actually based on the original experiment by Brenda Miller. So you can see that in day 1, the more times he repeat, although he didn't remember that he actually did the task before because he had lost his hippocampus, he was unable to form explicit new memories, like new semantic or new episodic memories. He couldn't do that, but he could somehow remember that performance of like how he did the task of drawing the star before. And you can see there's a steady improvement over the 2nd day. You can see that the number of errors he made steadily decreased. And this is alarming because it means that even without knowing any long-term memory, you can actually learn a skill. And one thing to note is that this is what HM learned, all right? But for normal human subjects, okay, they didn't really show it, but they did mention in the paper that human subjects learn faster. So they learn somewhat like this. This is my opinion of how normal humans would learn, somewhere like this. Like you learn much faster over a shorter period of time. Okay, because we are able to use the kind of prior experiences that we have learned before and try to boost learning. And so right now, this is the thing that I've been thinking about quite deeply recently. Like, where do we put memory in our current neural networks? because it seems to me that there isn't an explicit memory right now. So modern neural networks are similar to how Henry Molaison learned the star task. You look at the graph before here. It looks exactly like supervised learning. This is like how supervised learning error goes down like that. So it looks to me like modern neural networks are like Henry Molaison. They just use the procedural memory and then learn like experience after experience to refine it via the experience, but they don't really store like previous experiences for use again in the future. So people argued like, is storing weights considered storing memory? I mean, yes, there's a little bit of memory there. That memory is something like procedural memory that you gradually learn over time. It's slow, it's stable. Okay, you won't suddenly lose your procedural memory. Like, you know how to ride a bike, you won't suddenly forget how to ride a bike, or you won't suddenly forget how to play the piano. Like, there was another person who lost his hippocampus, I forgot the name, but he also couldn't remember who he was or like what time it is, but he could still play the piano very well. So that person is similar to Henry Molaison as well, but he can still like sort of learn procedural stuff. He could still have his procedural memory intact from the time he was playing the piano back then, but he couldn't remember and he couldn't form new memories. Okay, what if we can imbue this new memory formation and retrieval, so we can store memory and we can retrieve memory and use it to help our neural networks to learn faster? So this is something like episodic semantic memory. Okay, episodic is like you can learn previous episodes. Like previously I saw a snake, the snake came to me, I want to run away. Yeah, so that's like episodic memory. So the next time you see a snake, you can maybe instantly recall the memory that the snake wanted to bite you and you run away from it, rather than needing to go through this very slow procedure of the procedural memory, like doing through like experience after experience before you finally decide, okay, I should go away from the snake. Of course, there could be biological reflex as well, but assuming we don't have any reflex on this, episodic memory, the ability to recall past instances can actually speed up your learning because you can recall these instances and immediately do the action. Okay, in this case, avoid the snake. Same thing for semantic memory. If you know like the snake is beside the rubbish bin, then you will know that you shouldn't go next to the rubbish bin as well, because you can draw facts between them. So with all this knowledge, you can actually learn much faster with fewer information, because this kind of episodic semantic memory could be extrapolated to other scenarios as well. And this is actually what's lacking in modern neural networks. And we hope to bring something like this in, especially for reinforcement learning. Okay, any questions so far? So this is really the key aim of today's discussion: how to model this episodic semantic memory. All right. So the first thing is about abstraction. So I think it's quite cool because like neural networks, typically we like to say the neural networks can generalize across tasks, can generalize across input space. But my own personal experience using neural networks is that they can't. They can generalize quite well as in interpolating in the input space. So let's say if I were to give you like, this is a graph. Can you see the ink, by the way? Like,
yes.
Okay, thanks. So if you have a graph like that, okay, imagine your neural network, okay, fits this graph. So the neural network might fit it like that. Okay, let's say this is a like prediction problem. Okay, but the neural network, okay, may actually sort of overfit the training set. So this thing here is the training set, and maybe the original like trend is like one line like that. So you can see that in this small example, you can see that like neural networks are great for interpolation, not extrapolation. Like we don't really have a very good way to extrapolate to unseen data unless the unseen data comes from the same distribution as your training set. So this is the fundamental weakness of our neural network formulation right now, because it is a function fitting, and it basically tries to minimize the error of fit in the training set here, which may not lead to an extrapolating outside of the training set. Like I did experiments before trying to multiply two numbers. Like I was trying to model the multiplication function. So like I do 2-digit numbers like that, 12 times 24 equals to what? So this is a regression modeling using neural networks. And then the moment I change it to 3 digits, something like this, 1, 2, 3 times 2, 4, 5, or 1, 2, 3 times 24, Okay, the moment I change it to this over here, this is wrong already. So it can only work for like wherever I train my input, like 2-digit number, 2-digit number. So if you were to like want to code this out in the neural network, it is quite difficult to generalize. The best way to do it is to do it by procedures like, okay, take the first digit, multiply by the first digit and do the carryover. Then you do that kind of procedure, you can generalize to any digit length. Yeah, so I'm just saying that the traditional neural network doesn't really generalize quite well to outside of the training set if the unseen data is not of the same distribution as your training data. But how can memories help them? Memories can actually serve as a form of abstraction that can help to solve this generalization problem. Okay, let's see how. Okay, so this is the hypothesis. The hypothesis is that memories are stored in a very abstract form because we don't remember that well. You know, you try to recall a face, it can be quite bits and patches. Okay, at least for me. I don't know whether you can recall a face perfectly. Yeah. Can you? If you see a face, can you reconstruct in your memory how the face looks like? Or Evan or Shuchen, are you able to like visualize the entire face in your head if you want to reconstruct that?
Yeah. Yeah. I was just like something that came into my mind is like the face area is, in the brain is like distinct from like the text area in the brain.
Mm. Yeah,
Something
correct.
that I learned about recently.
Yeah, there's this whole area of the brain that if you remove it, you will not recognize anyone else. Yeah, because that area is specialized to recognize faces. Yeah, but even that area, my hypothesis is that it's not 100% pixel for pixel memory. It's just abstraction. Like you only remember it in a very hazy form, like key features like big nose, big eyes, that kind of thing. Yeah, maybe blue eyes, that kind of some distinct features, but you can't really remember everything clearly, at least for me. Yeah. So this is like one reason why I think like memories are stored in an abstract form. Maybe more concretely is like if you look at some experience of your life in the past, like maybe, I don't know, cycling on the beach, you can't really remember the full memory. You can only remember like bits and pieces, the more impactful ones. Yeah. So you store it in like some abstraction space, which is not the exact way you experience it. And maybe because of how you abstract like that, you can actually generalize. So this is the main idea. So the same abstraction can then be generalized across contexts. So this abstraction space over here enables the generalization. Then you fit in through the neural networks. Okay, so a lot of people have asked me like, why not use neural networks to do the first part? Okay, why not use a neural network to get the abstraction space as well? Yeah, so you can use neural networks, but there'll be a big problem later on. Because if you were to use neural networks to generate this abstraction space, okay, the moment this neural network changes, your abstraction space will change as well. Which means that if you were to store things in memory, your abstraction space will keep changing as your first neural network here changes. So I'm not very keen to put this as a neural network, but more keen to make it fixed. Okay, because like if you do a fixed way of generating this abstraction, you can actually store memories permanently. Like you don't have to keep changing your memories, which is a huge bonus. Okay, so like if you have word embeddings, like clip for images, somehow if you can have a fixed way to generate this into an abstraction space, that's great. For words, I think for images, I think it's immediate because we have a way to probably process it using the ventral cortex, the V1, V2, V3, V4. You might have a way to abstract already. For words, I think it's learned. So maybe the word abstraction space might be somewhere here. Like you have a basic way to represent like concepts in your head. And then after that, you have like some form of neural network to like train to match it to the respective words. Yeah, so there may be a separate abstraction space for words that is like higher level, that's trainable, but the basic over here is fixed. Yeah, so this is the hypothesis. So this is the hypothesis I said earlier. So the main advantage of this is that there's no need to keep updating the previously stored memories because the stored memories are in this abstraction space that is unchanged. So the more experiences you get in your life, you don't have to update like the millions of examples you experienced in the past because that will be disastrous. The amount of compute you need for that is disastrous. And you know, our brain, we don't really compute a lot. Yeah, we try to minimize computation. So this is the hypothesis. So with this abstraction space as input, the neural network can then take over the job and do associations. So neural networks are great at doing associations. You can look at transformers, they are great at doing associations. And that is one of the reasons why this neural network will take the abstraction space and then get it to the output space. So this giraffe thing here is inspired by my 3-year-old son. So when he was 1 year old, actually 1.5 years old, we taught him this flashcards. So the flashcards, there are different animals like elephant, pig, giraffe. So like a giraffe, this is one of the animals that he saw on the flashcard. Then we brought him to the zoo. Again, even without telling him that is a giraffe, he just pointed to us and said, this is a giraffe. Okay, so if you were to do like imaging, right, you will know that these two are different intensities of pixels, different like contrast and stuff like that. It's very hard to match both of them to the same thing, which is giraffe. But how come my son could straight away, without any prompting, know that the real life giraffe is a giraffe? So that got me thinking there, you know, like, how come we can do this and neural networks cannot do this? So perhaps there's a way to, like, maybe in the abstraction space, you can already store like different characteristics, like long neck, four leg, cartoon neck, that kind of stuff. Like, it may not be this kind of in words. It might be in concept space, which is like not in words. It's like a lower level than words. But I mean, I'm just using words here to illustrate. So maybe we already store this in some form of space. And then the moment that this giraffe is here, it kind of matches like a similar extraction space. And then you can get like the same output. Okay, this can be like a vector space. Okay, this can be like a vector space, like word embedding, that kind of thing. You can treat the abstraction space like a word embedding. Or I mean, where you have different in terms of your vectors, you have different like let's say this is what I'm drawing as a vector. Each of these units of the vector can be a different characteristic. And maybe the first one can be like long neck, second one can be legs, and so on. Yeah, so there could be a vector representation already, and it could be a fixed way of doing it. And then using the neural networks later on, okay, you can then get back like your output space, whether you want to have it like similar or different based on the context.
I have a question here actually.
Okay, yep.
Yeah, because I was wondering with like the word embedding approach, because like the definition of neck is sort of like relative to legs and body parts. And it's like there are like these properties are in relation with each other. And like how could a word embedding capture this process? Or
I understand. Yeah, the part hole hierarchy is not captured in word embeddings. It's not explicitly captured, but there may be a vector here for word part hole. Yeah, it's not natural in the current form of word embeddings. What you are talking about maybe is a hierarchical kind of like level where you have one embedding going to here and the other one going to here. So yeah, that is a limitation of the current word embeddings. Yeah, I'm not saying the word embeddings are the right way to do it. I'm just saying that the abstraction space is similar to how this is done, because you can then use like this thing here to sort of compare and contrast. So if there's a way to do like some form of hierarchy, that will work as well for the abstraction space. If we can have a fixed procedure to do that, like then we can have stuff like the bottom here will be like legs, and then over here will be like the body, right?
yeah.
And then at the top here we have giraffe. Is that what you're talking about?
Yeah.
Yeah, so I agree with that. Yeah, we might already be doing something like that, because like there's like, even if I scale up the giraffe or I scale down the giraffe, my kid will know it's a giraffe. Like so it's very, you know, the current like convolutional neural networks, they are not scale invariant. They are actually dependent on scale. So there must be a way to generate this abstraction space that is scale invariant, that is like more like relational abstraction. I agree with that. Yeah. So yeah, do you have any idea how to do it? You're chunking, is
I'm
it?
also wondering, it's also like a part that I'm a bit stuck on. And then one question is how dependent it is on 3D perception, like the perception of 3D space, or do you not need, is like 3D perception not necessarily needed for something to come up with this structural description? I feel like people must have asked this question before. and yeah, just didn't find the right literature.
Yeah, maybe there's a way to do like part-whole relations by just looking at like maybe different parts of the image, like here, 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 and then like each different part, they are like nodes in the graph, and then they get like categorized together. Something like that.
Yeah, yeah, I saw some of it in like unsupervised parsing literature. Like they basically try to parse an image into like parts and wholes. Yeah, but this part I'm also not so sure.
I think we can look more into it because this one, the abstraction part is very important because that way of like doing relational mapping might be already like how we store it in memory, because like in memory I also remember like things as scale invariant, so it must be some form of like relative size. Like I don't remember the giraffe leg to be bigger than the body. Like you don't scale only the legs, you scale the whole thing together. So yeah, there must be some way to store it. Yeah, and actually Hinton tried to do this. He had the network called GLOM, yeah, which tries to learn part-whole hierarchies. I'm not too sure how successful it was, but I have a feeling that the part-whole hierarchy learning, it might be already like a prebuilt mechanism. Okay, but what is that mechanism? That's the thing that we need to ask. Yeah, I mean the mechanism might be like something as simple as, I don't know, if you have current like word embeddings, like let's just take a look at word embeddings. You have current things called like clip. Yeah, if you already have a way to like generate like some form of abstraction like that, maybe you could already get like, okay, you will get the word vector straight away by having a fixed version of this like clip without it being a variable weight. You can get like word embeddings, and then what you can do is you can have like clip 1, clip 2 or something like that. Yeah, so you can get like a top level. Yeah, of course, actually I think in the brain is more complex than that, because we kind of have like the process of consciousness involves a few different parties talking to each other. Like for example, like you have one part of the brain light up and then you send to another part. This other part then goes back here, and then you light up another part here, and then eventually the whole brain talks to each other and comes to a consensus. So like maybe I'm not too sure whether abstraction requires consciousness. Maybe it doesn't. Yeah, but definitely if you want to do like some form of like, I think part whole kind of thing, you might need to do some form of like feedback loops. Yeah, so that's a topic for another day, because the feedback loops is something that I'm also interested in. We don't really have feedback loops in neural networks right now. Maybe RNNs is like the closest example of a feedback loop. But yeah, there's a lot of feedback in the brain. Like the neurons, actually about 90% I think are feedback rather than feed forward. Yeah. But that's an interesting point. Yeah. I don't know. Yeah, this is something.
Intuitively, to me, I don't think you need feedback loop. But also it's like, to me, the current neural networks, it learns abstraction, but it is stored in a very implicit way. It's like when you classify even as a classifier, like when you can like classify different species of dogs as a dog, then you are already like some abstraction is implicit, that has been learned by the network. And then with like the recent models such as DALL-E, that's they can, when you type a word like an avocado chair, they can come up with like an avocado shaped chair, then they must have some abstraction inside. Otherwise, they don't have this type of ability to merge the concept of avocado and chair. But I just find this is probably something very implicit that has been learned by the network.
Yeah, so they actually train it across a large amount of images and text and map it to each other using attention. So it's something like this embedding space. There's a common embedding space for the words and the text. Sorry, the words and the images. That's why you can sort of generate the image.
Yeah, and And then this abstraction space can be related to words as well, because it's like language is a way of abstracting, and then like humans sort of invented it for communication. But then when you think about it, it's like when you describe an experience using words, then a lot of information are being taken away, and then you're like arriving at one abstraction. So another possibility is that like you can achieve abstraction by mapping inputs to languages.
I mean, that's one way to do it, but I don't agree with it, because a lot of things that I can think about in my head aren't necessarily described by words. So I feel like the level of abstraction in our brains is slightly lower than language. Language is the express way of doing the abstraction.
Yeah, I think also
So,
just by language, I also
lower,
wouldn't
like,
be satisfied with the answer, but
it's
yeah,
the easiest to model right now because we have data for it. We don't have data about internal brain processes, but I believe the abstraction space is lower than language. Yeah, language might be somewhere here, like after the abstraction space in between the neural network, this is language.
yeah, maybe something like an autoencoder that but then autoencoder tries to like uncover the image, like something like a hidden unit inside an autoencoder, that you're learning something abstract, but it's also throwing away information.
Yeah. Maybe actually I'm a bit skeptical with autoencoders right now because, as I said earlier, like we can't seem to reconstruct a face properly in our memories. So I'm very
Yeah.
doubtful that we have an autoencoder like mechanism in our brains, because okay, maybe we do, because like you can have lossy reconstruction with autoencoders. Yeah, but whether or not your latent space is based on an autoencoder, I'm not too sure about that. Yeah, I mean, that's one way to generate it. I saw a few posters in NeurIPS that use latent space reconstruction loss to generate the latent space. Yeah, that's possible. Yeah, it seems too dependent on like how do you call it? Too dependent on the inputs. Yeah, so if we were to do a latent space loss, imagine if a reconstruction loss for a latent space like an autoencoder. I just wrote an autoencoder here. If you were to do a reconstruction loss in order to generate the latent space here, what will happen is with different input sources that you put in here, your latent space will keep changing, right? Because you will keep learning different kind of things that are important. Then if this latent space keeps changing, what this will mean for your memory is that you will need to keep updating all your earlier parts of your memory every time you have different inputs, which I think is impractical. Yeah, so maybe this latent space thing could be somewhere like at this part here after the abstraction space. But the abstraction space where you store your memories at, I think is largely fixed. Yeah, so yeah, that's that's my hypothesis. Yeah. Okay, yeah. Let me just clear this. Yeah, but definitely the part whole thing, actually it might even be done in the neural networks part. Yeah. Even like memory-wise may not be a part whole thing. It just might be like some like lossy version of what you get for your stimulus.
And also like a property about the part whole thing is that like if you see a cartoon giraffe and if you see like a real giraffe, the same part whole thing is being activated. So there is like something in common between the various instances. And then I'm just wondering if this like something in common can be used to describe what we're looking for. It's like every time when you see an instance of giraffe, either it's cartoon or it's like a fluffy animal giraffe, or it's a real giraffe, the same part whole thing is activated. And then it's like, is there some way to look for what are the same things that activate when you describe a giraffe as compared to like different things? And maybe this can be translated into like a loss function of some sort.
So I mean, the easiest way I can represent this like in current structure is like the word embeddings. So let's say you have like different balls here for your space, like different vectors. Like maybe your cartoon giraffe activates this field, and then your real life giraffe activates like this field. So then if we want to see whether is it a giraffe or not, okay, then maybe we will then focus on maybe just the first part here. So this might, we just assume that this embedding space might already take into account some form of part whole structure. All right. Okay.
Yeah, it's like the multiple instances of giraffe can be transformed by an abstraction projection function to a common embedding space. And that common embedding space is describing some properties related to abstraction.
Right. The embedding space you are talking about here is the abstraction space, right?
Yeah.
Yeah. So I do believe that we already can abstract it into like some form of common space already to interpret like all our stimulus into memory. And then from this common space, then whether we're going to classify for different tasks or not, it just depends on how the neural network does the association. So like what I draw here, like the first thing here is the like features of a giraffe, then both of them when compare, you will see that they are similar. But if like, let's say you are talking about cartoon or real life, maybe this is the last feature space here, which basically can then separate it. And the thing is, the key thing is, if let's say this whole thing here is unchanged, okay, this is the key thing, okay, if this whole thing here is unchanged and unchanged through life, what this means is that we will never be able to learn things that are beyond the representational capabilities of our abstraction space. So this is a very huge impact here. We are not able to learn things we are not built to learn. And I can give you some examples of this. We cannot see UV light. Okay, so that is something that like just from the rods and cones of your eyes, you cannot abstract like a class here for UV light because like we just don't have the means of abstracting it. We can't perceive it. Or you cannot like sense, I don't know, magnetic fields. Yeah, so you won't have that sense of abstraction space for magnetic fields. Yeah, so I think it's largely accurate because like, you know, you have what do you call that? Optical illusions. You have like the yellow-blue illusion where your yellow and blue can move together. Yeah, so that may be something to do with like how we saw our stuff in the abstraction space that cause it to feel like it's moving. Yeah, and that even though you know that it's an illusion, you can stare very closely at the optical illusion, you will never be able to change your perception. It will still appear moving to you. So I have this strong feeling that there are some things that we just cannot learn. And that's because we have a fixed abstraction space. Do you agree with that?
Yeah, sorry, I zoned out for a sec.
Yeah. No, I'm just saying that there are some things that we cannot learn because we are unable to abstract into a common space. Like things that like senses that we never used to have. Like
things that just doesn't doesn't go inside perception, then we can't learn. Yeah.
Yeah. So actually the abstraction space actually is linked to your perception, I feel. It is linked to how we get our stimulus. Of course, you know, David Eagleman, he did some experiments whereby you can imbue a sense of like sight by like using this vest on his body. Then it vibrates every time you see different objects, and people can learn how to like associate vision with the sense of touch. But if you think about it, you are still using the abstraction space for your touch, right? Because your touch sense hasn't changed. Your sense of touch is the same. You're just trying to map in the abstraction space, you're trying to map to a different thing called vision. So like you're trying to map your touch to vision, or for people who are blind but can still have their sense of hearing, there are apps that try to map an image into a series of tones. And essentially, we are not changing our abstraction space here. We are still using the same abstraction space because we are just using the abstraction of the audio and trying to map it to what we think it should look like in the visual space. Yeah, so I mean, there are examples of this that make me think that the way we saw this abstraction is just fixed and unlearnable throughout our lifetimes.
I feel like there is another component about efficiency here. Because actually, like when you think about it, there are multiple ways of describing a giraffe. It's like there are presumably a lot of ways to map these two instances into the same embedding space, but the mapping function could be different even across individuals, and some mapping can be more efficient than some other mapping. Like when you describe the giraffe as something with a long neck, then it can be a more efficient description compared to when you say that, oh, their feet are a little bit dark. So that takes longer time to recognize it's a giraffe. So to me, there is also something inside the abstraction space that like there are multiple ways of abstracting, but there are some abstraction that are better than other abstraction, and this better can be characterized by some form of efficiency.
Okay, I can see where you got confused already. Yeah. Okay, so I think I used the wrong example here. So like this long neck four legs cartoon, I agree you need some form of processing, okay, that can be very input dependent, because like what if you've never seen like real life giraffe or cartoon giraffe, right? So actually, maybe if I were to edit this slide, right, this actually should be like in the middle here. Like the description should be like a language part in the center, like halfway of the neural network. But the abstraction space will look like this. Will look like something like that. Like some like code, binary code that is like that is based on like how your sensory does the input. So maybe the abstraction space is in this like sub-symbolic level. Yeah, let's not talk about like long neck, four legs, all this, because all this I think maybe is at a higher order. But maybe at the lower level, like the abstraction space wise that like is common for any stimulus you receive is to just process it into like machine code or something like that. Yeah. Brain interpretable code. Yeah. So maybe the way that this stimulus and this stimulus is processed, okay, then from there you can actually generate like in your neural networks, you can then say is it similar or different. Yeah. Well, would that be a better description? Because I think we are trying, I think I complicated the language part inside here, language and attributes, which honestly, you may not learn how to abstract from birth like four legs, because you may not know what's a leg. Yeah, but what can be done is like you can visually like abstract away the scene, like maybe by doing I don't know, pulling. Yeah, you can do that as an innate mechanism already to get the abstraction space. Yeah, but you may not know there's four legs or long neck. Yeah, it's just that because of your way of doing like pulling or like some form of abstraction, you are able to then find similarities between these two inputs. Yeah. Will that be better? Yeah, I think that might be a better way to phrase it.
That's like before you find the common underlying components across multiple.
Correct. Right, and I've a strong feeling that your memory is using this to store. So you store this as your memory. Then, actually, come to think of it, maybe the way you do the mapping can change. Because if you store the memory as this code here, right? If you store the memory as this code, what will happen is that if you do an autoencoder process like what we were talking about earlier, you can actually learn a different kind of mapping based on the same code, because your autoencoder changed, but your memory doesn't change. You see, your memory about the giraffe is still this code. But as you grow older, maybe you learn that it's four legs. So you can actually learn four legs based on your environmental observation. Like slowly you see, oh, two legs, four legs, then your autoencoder might be able to get four legs here. So actually, that makes sense. Like you need not change the memory, but the way you interpret your memory might change. Okay, I don't know whether that sounds confusing. Like the memory itself is still stored in this machine code. Okay, but the way you interpret this machine code will change based on your life experiences. Then you can get like different like feature space in your neural networks. Yeah. Actually, in this case, the abstraction space very similar to like a pre-processing step. Yeah, you pre-process the image to 0 to 255 intensity, right? Before you go into a convolutional neural network. So this abstraction could be like processing it to like pixel space in 0 to 255. Yeah. This is something that I've been thinking about. Like, is your memory stored at this lower level? Or can your memory be stored like somewhere in the neural network level as well? Can you store memories of the intermediate representations as well? Or do you only store memory at the lowest possible level, at the lowest abstraction level?
Probably in multiple levels.
So you have different storage for intermediate and the bottom, but that's the problem again, you see. If you store it at the intermediate level here, what will happen is that, and if this intermediate level is like an auto-encoder reconstruction loss like this, then what will happen is that you will need to like re-update your memory each time you change your mapping. You see, because the memory will change based on how your mapping is. Yeah, so that's the issue. Do we change all our memories every time we change a mapping? Yeah, that's my only concern, yeah, for this part.
I mean, it's not a crazy thing to change memory when it's like a strange thing about memory is like every time when you try to remember something, then your memory about this thing also changes. So I think like if this part changes, then it's not like a outrageously crazy thing to me.
But if you remember and change your memory for like scenario A, will scenario B change also? Or will scenario B be intact? Yeah.
Yeah, I guess it can also be affected. Then it becomes complicated.
Yeah, so I mean, my gut feel just tells me that the memory is unchanging, but of course, later in the next few slides, I think I won't have time to do everything today. Maybe I'll just do half of it, and the other half will be another time. Yeah, because I think it's nice to have a discussion rather than just go through the slides. So what I feel is that like there's also a way to, like, when we retrieve and store memories in the current way that we store memories in the brain, we actually have a very unreliable system to do it, because like we still use some form of neural networks, which is basically changeable because of the way we have the weights in the neural network. We can actually change our memories, which is not ideal. So later on, I shall have a slide saying that actually maybe we maybe shouldn't use that neural network to store the memory. Yeah, so that one will be for the later part. But yeah, I think as of now, we can agree that there's some form of common space whereby you interpret the input in the common area, and then that common area will then be subject to interpretation by the neural network. So that's the rough process. And for now, I think I'm just going to keep it that the memory is at the bottom. Of course, there's memory at the top here as well. Okay, but how this is stored, I don't know. Yeah, how this is stored, I don't know, because it's, unless you can afford to change all your memories at the same time. But how this is stored is basically it will be stored in a very it's going to be a fixed way to store this. Yeah. Okay, I think we can leave it as that for now. If I got some people in neuroscience, I will ask them whether they think your memory can be stored at multiple. How do you think memory is stored? I think it's quite interesting. Okay, shall we move on to the next slide? Okay, so the next slide is an example of like maybe how the abstraction space can be generated. So for example, in a pixel image whereby you only have two pixels now, like yellow pixel and the blue pixel, like maybe you can perform some form of abstraction to like pooling. This like a pooling, like you pull like these squares together. So this is what I was saying earlier, that like if regardless of scale, okay, you should be able to see a giraffe at a small scale or large scale. So one way to do it is to like do part whole hierarchy and then get the giraffe relation structure out. The other way is that you can like do the scaling inherently in your abstraction. So you can like do like abstraction like that, then eventually you store it as like one square. Like same thing for this one square, because regardless of you observing this one or you observing this one, okay, these are two different scales, but the end outcome is the same. End outcome, you still see one yellow square. So the abstraction process in this case helps to generalize like across scales. So like, for example, you have a 4x4 square here or 2x2 square, you will interpret them as the same way in your abstraction space. So this recursive manner of abstraction is very important, because you can then use it to interpret multiple different kind of stimuli in the same way and store them in the same thing. I mean, you saw a big giraffe or small giraffe, you should store them roughly in the same space, unless you're talking about size, which we actually don't remember that well anyway. So, I mean, I think this recursive abstraction is correct. Then also, this is another thing that might be done. Okay, so there's this hierarchical chunking thing that Shuchen, you presented at NeurIPS as well. So maybe if you could do this implicitly for every kind of stimulus. So not like the method you presented, like this hierarchical chunking is already known rules. That means the rules are already known. It's like an algorithm. You just execute the algorithm. Then maybe you can use it to recursively get the abstraction space.
How
Right?
would it work?
So it's something like this. Like let's say you have a rule like this, like two numbers similar, then you just add one and store it. So something like this would lead to a rule like this. Let's say you have 1 1 1 1 1 2 2 2. What you'll get is you add 1 to this, so this will become 2. Then this one will become 2 1. Then this 2 2 will become 3 2. So it will start like that, and then 2 2 you add 1 will be 3 1 3 2. Yeah. So like in some sense you are like performing some form of compression. Yeah. So the chunking in this sense is the idea of like recursively simplifying your input stream into one common space here, like that, like compression.
Mm-hmm.
Yeah, so this is a fixed rule that is unlearnable and unchangeable. So you don't need to do statistical like probability distribution or like hypothesis testing to test out which one is the rule. It's already a fixed rule to compress stuff that might already be present in our biology. Yeah, so it's very similar to like this abstraction of this majority mapping. You can actually do this like to do some form of like chunking to make your input smaller. Yeah, in a recursive way. Yeah. So yeah, then like if you get 3 1 3 2, there may be different ways to get this 3 1 3 2, but it doesn't matter because like if your algorithm for doing this is correct, you will be able to chunk similar kind of concepts together in the same abstraction space, and then you interpret them in the same way. Yeah, okay. I hope it's clear. Yeah. But anyway, this is just an idea I have. I haven't really tested it, but I think this would help greatly with memory storage if this is the case. Yeah, because I'm not too keen with using neural networks to do the abstraction and store it in memory due to the issues I said earlier about like needing to re-update everything. Yeah, unless the re-update procedure is very fast, then we can consider that as well. Yeah. Yeah, so the other thing that I was thinking about is that there's this thing called lossy abstraction, which is the same, like we can use the same abstraction process again. You can see that like this input and this input can be mapped to the same output. Yeah, so in some sense, this is actually good because if we were to we want to find out where are our right-hand edges, like this L-shaped edges. Okay, it doesn't matter whether L-shaped edge is like slightly to the bottom or slightly to the top here. We want to view them the same way so that we can like generalize better. So one way to do it is to do like lossy representation. So this is the way that we can do it for like images. So actually the pooling layer is very important for like convolutional neural networks for generalization. Yeah, if you remove away the pooling layer, like what most modern architectures do, you won't generalize as well. You will need a lot more data to compensate for it. So I think this lossy abstraction thing is quite an important idea. And if it also means that the way we represent our experiences in our brains might also use this kind of lossy abstraction in order to generalize better. Like it's how do I put it? Like, okay, let's say you are late for school, all right, then you can like, because like how you contextualize your whole experience, you can like loosely like think of it as late. Yeah. Then you can generalize it to late for work, late for a meeting, and so on. Yeah. If you were to store every detail of you being late for school accurately, you will remember like running for the bus, entering the school. It's very hard to generalize that context to another context. Yeah. So there must be some form of way to like not store all the details, but store only like the overall broad strokes of an experience. Yeah, and that's what I was thinking about with lossy abstraction. Okay. Are you all okay, by the way? Yeah. Yeah, all right. Let's talk about this point. Then after that, I think we can call it a day. So so this is basically the one that I was thinking of, like how we can like retrieve our memories that can be how can our memories be retrieved such that it can generalize across different situations as well. And actually one of the key things for doing it is perhaps the multi-modal system, where basically you can store memories from different input stimuli like visual, audio, sensation like touch or pain, spatial like location. So you can take all these inputs and you can store them in a compact form for your memory processing. And yeah, this is the thing that I was thinking of. So like for your memory, you can have a key inside here, and then you can process your memory and out comes the value here. So like you can retrieve your memory from like a key value mechanism, whereby your input to like a neural net is the key and the output is a value. Of course, there can be other mechanisms where you can use like Boltzmann machines, and then you can like put a key here, and then based on like the interaction, you can get a value. Yeah, that might be interesting also to investigate whether this can work, because I've seen quite a lot of people in the memory workshop use autoencoders. I haven't really seen, sorry, not autoencoder, Boltzmann machines. I haven't really seen whether this kind of thing is superior to like this kind of key value approach. All right, so let's say we can like model this as two different ways to like retrieve memory in the brain. One thing is that if we were to do this key value like retrieval approach, as where the key is the input and the value is the output for the neural network, it may not be ideal. Okay, it may not be ideal to retrieve your memories this way, because if we learn other key value pairs, you see the weights used here are the same. Same thing for this Boltzmann machine. The weights used in the nodes are the same weights. Okay, if you were to learn a new input, what might happen is that you might update the weights here, and then you might affect the value for your other output. So for example, like this, let's say, okay, I don't have to draw the table. I have a table down there. Let's say if we have like a hash table already done like that, we see visual A and visual B. Like visual A, maybe like Monica's house, you relate it to Monica. Visual B, Joey's house, you relate it in Joey. Okay, this is actually from Friends. Okay, these names are from Friends, the sitcom. All right, then we have visual C here. Okay, let's say we learn visual C is like Rachel's house. We map it to Rachel. If we were to do it in this kind of mapping way of a neural network, what might happen is that, you know, you may not be able to map it that well. Okay, because when you update your visual C to be Rachel, like you update the weights here, maybe visual B here, instead of Joey, you will remember someone else. Like it becomes like Ross. Yeah. So the way if we were to use a neural network mechanism to store your memory like that, what might happen is that you will have the problem of shifting key value pairs. Like your earlier key value pairs may not be constant anymore, because you update your weights, it might affect the earlier key value retrieval. Actually, this is a problem with the neural networks learning as well, because like in reinforcement learning, you try to learn different keys to different values, but because of the way like you use the same network for everything, what experiences you learned in the past might not be like stored properly, because when you update the weights, your previous experiences might change also. Yeah, so I think this is not ideal. I feel like the more ideal way is to like have a hash table. So you can actually model your memory as a hash table like this, and then you store each value to a key. And what will happen is that you will probably have no memory retrieval issues, okay, except for collisions. So for collisions, it means that you have two situations that refer to the same key again, okay, but the two situations are different. Yeah. So in order to handle that, one way to do it is to like have a better way to generate the key so that you avoid your collisions, which is possible because a multi-modal input has a lot of permutations you can play with. Yeah. And the other thing is like, let's say if you want to stick to the one key, one value approach, like a like a neural network, if you only have one key, okay, your key must always give it the same value. Okay, this is the modern neural network approach. Okay, if you were to store in a hash table, actually one advantage is that you may not need to have the one key, one value approach. You can actually have like visual A here linked to something else, like linked to maybe, I don't know, Rachel again. Yeah. So you can have another key value pair that is using the same key, Okay, we can store this key as a separate value of the hash table. And then when we like query, we can return 2 results. Yeah, of course, how to interpret these results is a separate thing, but the advantage of using a hash table is that you can store more than one value per key. Yeah, and this, because I was thinking about like how to model like probabilistic interactions of the world. Yeah, if let's say you have one state, you move to another state, yeah, you might need to have two separate rows of your hash table to model that. So I think the hash table approach here is the superior one because it doesn't suffer from memory forgetting. Like this doesn't change. Okay, you won't have the changing thing like a neural network does. And you can also model multiple keys to multiple values. Yeah, so this is the hash table approach. Yeah. Shuchen, you have anything to add? Because I think you were the one who talked to me about hash tables initially.
I think there can also be it's like a nested structure inside the hash table.
Okay. Wow, how do you do that? So you have a key that goes to another key, that goes to another key value table.
Yeah.
Oh yeah. Then you can do like hierarchical kind of key value, right?
Yeah. And that would speed it up quite like because there can be multiple keys that goes to the same value.
Okay, yeah, because the value will be, it's something like a grouping, right? So like you can group all of like visual A into this key value pair. Then over here you can then look at the sub key, right? Then you can look at like maybe sound 1 or sound 2 or audio 1, audio 2. Is that what you're talking about? Like you can group by a certain header first. Then you from the header you go to a sub table. Is that what you're talking about?
More like I don't know, it's like to me like the key and value are not so absolute, but they're like related to each other, so it's more like they're a graph, and then in this graph it's not necessarily that you only have one edge between key and value, but rather like the keys, and like for example Monica can have like multiple houses, so so the same value can correspond to multiple keys.
Okay, I mean the same value can correspond to multiple keys. That's fine because you can match different keys in the lookup table with one instance, one query.
Yeah, and also the same key can map to multiple values too.
Okay, no, but you don't retrieve things by the value, right? You retrieve things by the key, right?
Yeah.
So it doesn't matter whether you have like a mapping to any value, right? Unless you are talking about a bi-directional kind of mapping, like this one map to this one, and then the other one
Yeah,
map back.
that's what I was thinking actually.
Yeah, I think that will be difficult because if you map the value back to the key, it will mean that you can have a lot of conflicts. Let me think about it. I mean, why do you want to map back though? Why do you want to map the value to the key?
Because sometimes you are used, like when you look at like when you want to think about what does Monica's house look like, then you go from Monica to the house.
Oh, okay. You're talking about from the person you map to like related things. Okay, that I understand. So it's like a relational map. Like basically you think of a particular thing in your memory and then you can like look back and like find the related instances.
Yes.
Yeah, but in that case, I can answer your question using this. So let's say you are talking about looking at Monica, right? So let's say remember this is Monica's house. So you can also associate it with like maybe Monica's face, okay, as a key. So maybe there will be a separate key whereby this is the key as well. Yeah.
Yeah.
Yeah. I mean, I'm just using this value as a name for easy reference, but the value that I was thinking of for the like reinforcement learning side, the value might just be like, what's the next state? Yeah. I'm just thinking, okay, let's say if I were to think of my memory as such, right? If let's say my key is my state 1 and my value is the state 2, which is the next state that I transit to, do I, from a later point of time in my life, when I look at a particular slice of my life, can I link it backwards? Can I remember backwards? Like, for example, if I walk from my house to my train station, if I start at the train station, can I reverse and like, can you reverse your memory and imagine yourself walking backwards?
Like backwards in terms of
Can you imagine the events unfolding backwards in time?
okay, so I can't imagine that, but in neurons it has been observed that like they do preplay and replay. So one of the more interesting thing that neuroscientists has observed is that, like, for example, when you show a maze to a mouse and then make the mouse go from like the beginning of the maze to like a reward location, then and then after this mouse has been practicing this pathway for a while, when you look inside like neural activities, then you see that like the representation of the path can be played backwards before they make a decision.
Yeah, definitely. No, I mean, I also do some research into that, the pre-play and replay. What I was thinking of is that the pre-play is the one referencing this hash table. Okay, get the key and get the value, and then you can get like state 1, state 2, state 3. So you are like replaying your memory from the start. Because I myself also cannot remember myself walking backwards. I can remember myself walking forwards, and that's, I think, because of a correlation between successive time steps like that in your memory. So you only store memory like based on the time that you experience it. You cannot retrieve your memory like that. You cannot retrieve from the last state, you get back the earlier states. What you have to do is you have to start from the start and then you go all the way to the back. Then what happens during pre-play, I believe, is just to get this sequence of states, which you can store in the memory buffer. And then we can just access the last state and access this state, access this state. And why do we do so? It can be for credit assignment, or and it also can be for like learning of like a neural network, which actually in the later slides I got talk about like fast and slow network using replay like that. Yeah, so this is, I think, the key reason why I don't think the value can go and reference the key, because like I don't think we can imagine things backwards. Because if let's say we have temporal associations between the key and the value, just from the value alone, I cannot remember the earlier time state that I was in. Yeah. It's the same thing for like, ABC, right? A, B, C, D, E, F, G, we memorize the alphabet. You can memorize it forwards. But if I ask you to recite the ABC backwards, I think you have a very hard time to do that. Right? Or you imagine your phone number, you try to remember it backwards. Yeah,
it's really hard.
Yeah, it's very hard. I mean, I can do the alphabet backwards because I memorize it backwards for competition before. Yeah, so that's different. But the thing is, if we want to do like a key value mapping where the key is the start state and the value is the next state, I don't think we can reference the value and get back the key. Yeah, that's my point here that I was trying to make. Yeah, maybe there can be other key value mechanisms that allow you to reference with each other. But as of like what I was thinking of for memory, especially in reinforcement learning wise, I think maybe you can't do that. Yeah, but for other cases, maybe you can. Yeah. Yeah, I mean, I hope that answered the question. Yeah. Yeah, I mean, I'm more of like a key to a value kind of person. Yeah. But yeah, I mean, there could be other mechanisms. But for the purpose of like whatever I have in mind here, it is strictly from the key to the value, but you can have multiple keys of the same kind. Like you can have visual A here also. So in the earlier iteration of my idea, you can only have one key to one value, but I changed my mind. Okay, because to store probabilistic transitions, you may need more than one key. So I allow for more than one key now. Okay, then the question is, if we have more than one key now, how do we get the value, right? Imagine you have one visual A that is Monica and one visual A that is Ross. If you query your neural network or query the hash table, okay, I see visual A now. So this key here is actually the abstraction space. Like the earlier part, we talked about recursive abstraction, lossy abstraction. We get this abstraction space. We query the hash table now. Okay, I have visual A. So what do I see? And the network will be confused now, right? The network will have, oh, there's Monica. Oh, there's Ross. Who should I reply? Like, so that will come into the next part. Okay, where we can actually have like some form of averaging of the responses. Okay, so I'll move to the next slide. So, okay, sorry, we haven't gone there yet. But the next point is like this is about single hashing. If we have multi-modal input, we can also have multi-modal hashing, where your keys to the neural network or keys to your hash table are multi-modal features like visual A, location A, and so on. So yeah, you can have like, this is the multimodal hashing. And then basically you can actually reference like a subset of this to extrapolate to unseen settings. So for example, I give you an example like this. At location E, which you know is very similar to location C, okay, you will actually like look at this one here. And then you will know that, okay, this is Joey. So just from the location alone, without the visual cue, just knowing at the location, you already know this Joey. So this location can be something like place cells and grid cells in the brain, where you really roughly know where in your immediate surroundings, where are you. Okay, so for like visual D, similar to visual C, okay, without even the location cue, okay, just using the visual cue, okay, we can already extrapolate that this one will be Rachel, because like this has been what we encountered before in the past. Okay, if you don't have this kind of like multi-modal hashing like that, you want to learn this in the neural network weights, it can be very tricky because you will need quite a long time before you can like store all this reliably in your weights. But if you store it as a hash table, it's like immediate. You can like reference your past encounter. It's like doing a k nearest neighbors matching to your neighbor node, and immediately you get your answer. Yeah, so that's the beauty of multimodal hashing. And you can only use like one mode in order to get the answer. Also, of course, with more modes, the more accurate you are, that you can extract your answer. So what if you have more than one key that reference the same thing, right? So that's the next slide. Oh, sorry, that's 2 slides later. Yeah, but yeah, let's just go through the slides first. Later I thought on how to get the value from more than one key. So like with incomplete multimodal data, okay, so incomplete multimodal data might be because like maybe you are blindfolded, you don't see your visual input, but you know your spatial input. You can still like sort of roughly tell where you are, okay, through this thing that I term incomplete hashing. So this one I came up with this term in NeurIPS while talking to Shuchen. Yeah, so this incomplete hash is like you only have a subset of the input data, but based on the subset, like let's say you only have visual or you only have spatial, then you can just like reference like a subset of the table here in order to make your decision rather than referencing the whole table. So of course, the more modalities you have, the larger the table you get the reference, and then you get a more accurate result. But if you have only a subset of your features, you can reference a subset of the table like that, visual and spatial. Okay, so it's very simple. It's something like just basically like doing a filter. you only filter for visual for this part, and then you only filter for like spatial for the other part. Yeah, it's just an example. Okay, so just one part of the stimulus can already match to the nearest in memory. So some examples of this in real life is like this. When we look at our past photos, okay, the visual cue, we can already trigger the memory of the event. Like just looking at your photo of maybe I don't know, your graduation, you can imagine your graduation party, something like that. Let's say you associate a particular piece of music to a certain person. Just listening to that music, you might already remember that person already, because that person and the music is linked together in your memory. So this is one instance where you can just use only the music to reference that person. This is very notable. Like sometimes you have this thing called nostalgia, right? Like you go past a particular location, and then after that, all your flashbacks of memories of what happened at that location. Oh, it's my old school demolished already. They remember your school days. So this is actually quite notable because like we have this system whereby you don't need the full value of your multimodal hash. You just need one small little section of it, and you can already do like some form of filtering and get the value out. Yeah. So yeah, Shuchen, this one is more elaborate than what I was talking to you about. But do you agree with what I'm saying here?
Yeah, I'm just thinking about like implementation wise, how would it look like?
Say again?
Like, so you would implement it as like a hash table, and then like with the specific modalities as like separate hashes.
Yeah, okay, you're thinking about how to reference the table, right?
Yeah.
Okay, so that will be the next slide. Okay, let's move on to the next slide. So I like to introduce this idea of multiple referencing. I really like this idea. So this allows us to, if we have like multiple like queries, like over here, visual A, location C, you see, you can match to visual A, or you can match to location C. So all these are matches of 50%. So how do we know what is the answer, right? So the thing is, you can query the visual part, or you can query the location part separately, you get different answers. Or you query this visual A, location C part together, you get separate answers also, because if you query two together, you know, the similarity, I mean, you might be, if you can store this into an embedding space, you might be able to use like cosine similarity to do this. Yeah, you can actually get a like percentage match. And then what I was thinking of doing is, you can do something like what a transformer is doing, the query key matching procedure. Okay, where you take the softmax of your query and key, like basically this is QKT is Q dot K. QK key is the same as Q dot K, where Q dot K is equals to, okay, Q dot K is equals to, the dot product between two vectors is equals to the magnitude of the vector Q times the magnitude of the vector V, or the vector K, times the cosine distance. Yeah. So actually, in some sense, this is like a proxy to cosine similarity between the two vectors. Yeah. So yeah, you could do like some form of like this kind of procedure, cosine similarity. Like over here, they just divided by the embedding. This is just a normalization term, but you can omit this also. Yeah. So you can just see how similar your query and your keys are. Okay, and then do like some form of softmax so that you can get a weighted sum. Okay, you can weigh the value written. And in this case, if you have 50% match for all of them, all this will be weighted the same way as 1/4. And you can see that Monica appears how many times? 1, 2, 3 times. Monica appears 3 times, Joey appears 1 time. So if I were to query visual A, location C, what I will get is I'll get Monica as my answer, because Monica appears more often. And if you do a weighted like key retrieval using some form of like similarity to your query to weigh your written value, you are able to get like a certain value out from this multimodal hash table. Yeah. So if even you have multiple keys, like you have two visual A or two visual B, and you query a visual A or query a visual B, even you have two similar keys, you can still get back the result from your hash table, because you can do a weighted averaging. Yeah. Or I mean, if let's say this value here cannot be averaged, if it's like a category, you might just do a majority voting. Yeah. Okay, so the any questions so far for this?
So you're suggesting that it can be integrated into the attention mechanism.
Yes. So we use some form of attention mechanism to retrieve what value it should be, because we can have, the hash table can have keys of the same value, multiple keys of the same value. Yeah, I mean, why this is the case, actually, I thought of a mechanism for the reinforcement learning part. Quite interesting. I just thought of it like 2 or 3 days back. I'm not even sure whether it works. Yeah, but I'll share with it. I'll share with you on another setting. Yeah, because I think I don't want the meeting to last too long. Yeah, maybe I'll cover a few more slides and we call it a day. Yeah.
Yeah, sounds good. But this point is really interesting, because yeah, I also had some trouble interpreting the attention mechanism, but now, like under this context, it starts to make more sense.
Yeah, I really like the attention mechanism. I myself find the transformer model overly complicated, but the attention mechanism I find is correct. I think attention is probably the only thing I like about the transformer. But I mean, the paper is called All You Need Is Attention, right? Yeah. So I agree that attention is important. Yeah, but I think there might be more than the structure that they are talking about, because you see the structure that they use doesn't have a hash table like this. It's all implicit in the weights or the memory stored. If we can store an external hash table and then reference it properly with the key query procedure, I think it will give better results. Yeah. But I mean, they are using it for different contexts. They are trying to use the attention of self-attention to like model the embedding space of the words to be more separate or more similar to each other based on the context of the sentence. So that's the use case for theirs. But the use case that I'm thinking of for this memory thing is really to, based on your previous experiences, find the closest match such that you get the most similar like value. The value can be like your next stage or your next action. Get the most similar value that you need to do in order to be like optimal or to do something like as per what you have done before. Yeah. And if you don't have this hash table, imagine if like Henry Molaison, he doesn't have this hash table because he doesn't have hippocampus. Imagine if you don't have this hash table to like tell you like what's the next action you should take. You have to learn everything like through your weights, you know, the weights of the neural network, which will take very long to train. Yeah, so I think this is the key to improving neural network speed, having a separate hash table, and then using this hash table to store relevant experiences. And then after that, referencing this hash table in order to speed up your conversions to the right actions. Yeah. So yeah, anyway, I would like to just touch on this last point here. So this last point here was motivated by this thing called random forest. Are you familiar with random forest?
I've heard about it before. I think I used it a long time ago, but now I forgot about it.
Yeah. So random forest is like that. You can have different forests. Basically, it's a decision trees whereby you have each decision tree. Let's say you have input 1, input 2, input 3, and input 4. As in, these are like categories of your input, like different input types. Maybe in the first decision tree, you only use like 1 and 2 to make a decision. In the second decision tree, you only use like 1 and 3. So you use subsets of your input features to make a decision. And then you use like over here, you use 3 and 4. So the idea is that because if you use subsets of your input features, you will probably not overfit. Okay, you will learn how to like find a good classification with this few input features, this few and this few. And then eventually you have 3 different outputs, right? What you can then do with this is you can then do voting. Yeah, majority voting or something. So it's been shown that if you do like this kind of random forest, you will have a more robust prediction compared to you just using the full like query, full input features to get the query. Because sometimes you might, sometimes that particular experience might just be like an outlier. Yeah, so if you were to do like more robust, like over here, this input things I'm thinking of is like different modes. You select different modes to query your hash table. And that will likely lead to a more robust kind of performance because it's been shown in random forest that is better than just using like all the features at one go. Yeah, so this is the last part here. This is different from transformers. Transformers doesn't do something like that. At least I don't think it does so. But I think if you were to do that, you will have a better memory retrieval process. So yeah, actually this slide is quite important because like a lot of ideas come into this slide.
Yeah, that's really interesting.
Yeah, just a disclaimer, I haven't tested it out yet, but I'm going to do something like that. We can probably test out without this thing. I think it will still work. But this one is for if you have a robot with multiple stimulus, like visual, audio, location, and also maybe like the wheel velocity, wheel angle, that kind of thing. Yeah, you can have all this, and then you can like perform some form of retrieval of past experiences using some form of subsets of whatever stimulus it has. Yeah, so this part is just my own hypothesis that this will make it better. Okay, Yeah, maybe I do the part on the emotions one first, then I conclude there. Okay, because this is like, how do we store and how do we forget our hash table, right? This is important because a large part of learning is forgetting. Like if you store all your experiences, like there are some people in this world that can never forget, or they forget at a very slow rate. And what happens is that they become so inundated by their experiences that every single object they hold, right, they imagine and remember all the past instances that they hold that object for, which eventually lead to them being unable to function properly in life because you will just be too overwhelmed by your memory recall that you can't make a decision. So like learning how to forget is very important. And how do we store and how do we forget? That's an important thing that I'm thinking of, because we need to build this hash table here with the relevant experiences, okay, so that we can interpret our current situation properly, okay? So the key point is like, one, there's limited room in the brain to hold memories. Okay, we need to be selective as to what can be stored. So in the typical, in the typical key value neural network approach, you have only one key, store one value. But over here now, I'd like to say that nope. Okay. Yeah, this is as of yesterday. Okay, I was thinking about it. No, I don't think this will work. Okay. What will happen is that we can have multiple instances of the same key. Okay, so this is not an issue as to why you need to be selective, but you need to be selective as to what you store because there's limited room to store this memory. Yeah, we can't store everything. We have limited like hardware to store it, or your brain space is limited as to how much you can actually remember. So how do we know what to store? What are the more important things to store? So this is my theory. My theory is that what you store is highly linked to emotion. Okay, because it's true. Okay, I mean, my wife, right? Okay, I'm gonna say something that she might be a bit upset, but she remembers all the stuff that I did to her that made her upset. So every time, you know, when when you talk about stuff, sometimes you'll bring up like stuff from 10 years ago saying, oh, you know, last time, you know, you did this, and I was upset. Yeah. But you know, all the other cases, she doesn't remember that clearly. But the times that she was upset, definitely remember. Okay, I don't know about you, but I think emotion plays a huge role in storing memories, because like my past memories also, I remember cases of myself like being bullied more clearly than myself like studying. Yeah, because like if you feel strongly about an emotion, you sort of will like remember that memory more strongly, and that memory doesn't like go away that easily. Yeah, like flashbulb memories. Flashbulb memories are like incidents whereby like 9/11, the World Trade Center collapse. Where were you during 9/11? So researchers have asked people that way also, and they realized that they can remember quite clearly what they were doing at the time of 9/11. Okay, so this is an idea, or like Kennedy's assassination. Yeah, very high impact events to the US population. People can remember what they were doing at the exact moment when the news report was reported. Yeah, but maybe for Singaporeans not so much, because like maybe too far away from the US context. But like for Singapore, maybe it's like when what were you doing when Lee Kuan Yew died or Lee Kuan Yew passed away? So those kind of memories might last for a long time, and is probably linked to emotion as to how we store that memory. So like if you are very happy, very scared, or even very surprised, okay, you might actually store those memories better. As to how to model this, I don't know, but the hypothesis is that you will have to store this as a high priority, okay, such that maybe each memory is given a strength, okay, and then like every time step the strength minus 0.1 or something. So for those like memories that are very strong, like those very sad memories, okay, or sad memories, your strength maybe is like 5. But then for those normal memories, your strength like 1. Yeah. So you will take a longer time for the sad memories to be forgotten. Yeah. But the normal memories very fast will be gone. Yeah. So this is like how I was thinking of, like in school settings, you normally don't remember your process of how you studied, but you remember like your friends and how you hang out with them. Yeah, because those give you a higher like emotional state. Yeah, and you tend to remember those. Yeah, I mean, I just take your comments on this? Do you agree with this way of storing memories? Evan or Shuchen? I mean, either one can just say.
I mean that should be the way. It's yeah, I think that should be the way to approach it.
Yeah, thanks. Yes. So actually, before I was thinking about this memory thing, I was thinking like maybe we can model AI without having any emotions. But I have a feeling that intelligence is highly linked to emotion because there's so many stimuli in the world. How do we know what is important? So the emotion regulation can actually help us to tell like what are the important things. Like if you're very scared of something, like you stand on a plank on top of like rain stories drop, you will remember those instances because like this is a matter of life and death. So like your circuitry will tell you what's more important. Like fear is a very important emotion because it's typically related to life and death situations. You want to survive. So these memories are very important to be preserved. You see a snake one time at this area, you better remember the snake is there because you don't want to go die there again and get eaten up. Yeah, so stuff like this. So yeah, that's for the storing of memories. Another thing, okay, I was recently reading a book on memory. And this book says that like you can actually learn things more easily if you use your attentional focus on it and remember more of the details of what you are looking at. So you can force yourself to remember memories because of you paying more attention to it. So while that is the case, I don't intend to model it here in AI because I think that's a limitation of the human body. Like we just cannot attend to so much stimuli at the same time. But in AI systems, you should be able to attend to the stimuli at the same time. But you can then choose what to store in your memory. Yeah. So I think this part of attention and how much you can remember based on attention, probably not needed to model in AI. I might be wrong, but I think probably not needed. But what is needed is how long to store this memory. Okay, because we don't want to store the memory for too long. And then like when the situation changes, the memory is irrelevant. Okay, we want to forget. So this is the next slide on forgetting. So we want to forget our memories, okay, because those not relevant, not accessed often, they're often forgotten and make room for other memories. So it basically makes sure that the hash table that we have, the key value hash table, okay, is of a very condensed form that is more relevant to the environment. I mean, you can treat it as like a sliding window. Like, you know, the sliding window thing, like you have a series of like states, and then you just like condition your next state prediction on the last three states. Yeah, this is what they do for stock market also. Yeah, you condition on the last few time series and predict the stock price. Yeah, so yeah, memory, the mechanism of forgetting is something similar to that. After a while, all your memories of like your hash table here that is not accessed, okay, all these memories here might just be deleted, okay, because after a while you don't access them, it's gone, okay. And this helps us to stay fresh, okay, because like whatever happened 10 years ago may not be relevant to what is happening now at this moment. Yeah, so eventually the memories will decay, except very high emotional memories like a snake or I don't know, what were you doing when I want, you know, those kind of emotional memories, you hold it there because those give a very high priority and that might be important even in a very long time in the future. Okay, so actually memories can also be stored longer and longer depending on how often you access it. So if you access your memory more and more often, so there's this guy called Ebbinghaus. Yeah, so Ebbinghaus came out with an experiment. He created a list of very difficult words to memorize, like non-existent words, nonsense words, and then he himself was the experiment. So quite amazing. He also every day he took this list, I don't know how many words, 100 words. He started to memorize those words one by one, and then he reviewed like, okay, how much do I remember after a few days? Then after that, he revised again, and then he realized his retention rate improved. The more he revised, the longer it held. So the thing is, the more you access your memories, the stronger the connection. So like the first time you access it, maybe the strength from 1, the strength of the memory can go to 2, and then you revise it again, you can go to 3, which is quite an interesting mechanism because if you think about it, memories that are accessed more often means what? Means it's more relevant to your situation right now. So we increase the strength of your memory each time we access it so that we know that, okay, this memory is important, don't forget it. This memory is even more important, don't forget it. eventually it might reach a state that you will store it forever. Yeah, because you access it enough times, you might store it forever. Yeah, so this is I think this is a very interesting idea, because you let your experiences decide what you store in your memory and what you keep in your memory. And the more times you repeat it, the more likely you should keep in your memory for a longer time. So quite cool. Yeah. So frequently used memories are strengthened. Yeah. Okay, I think that's more or less it for the day. Yeah. Do you have anything else you want to add? I think I will. Oh, sorry. Maybe I do one last slide. Okay, intermemory linkages, because this is something that is related to what we talk about in terms of the predicting of the next state. So I have this hypothesis that if two memories are highly related, they will be linked together via a directional mapping. So like, for example, state 1 to state 2, if it's like temporally related, there will be some linkage that once you recall state 1, you can link to state 2. So this can be a key value pair. Okay, it can be stored in a key value pair, or it can be stored in a directional graphical network like that. So I haven't figured out what is the best way to do it, but it's either a key value pair or a directional graph. Yeah, so if you trigger one memory, you trigger the next and the next and the next. Yeah, so sometimes if you think about it, like if you like walk by like a particular building and then you recall your memory, it's natural. You can't stop the memory from being recalled. You'll just keep like playing in time sequence, like, oh, this school is the place that I had like my first date or something like that. You can recall your memory like that. Yeah. And that might be the result of like some key value mapping or some form of directional graph that you flow through the graph like that. Yeah, so this is I feel this might be one of the reasons why we need to do pre-play and replay, because the pre-play step gets all this next state with associations in order to like do the replay step. Yeah. So like what we're interested in is the backward replay step, but we need to do the forward because it's a directional graph like that. You cannot like read your graph backwards, or you cannot read the value and map to the key. So yeah, this is a very important point of why like maybe hippocampal replay is the way that it is right now. Yeah, maybe I just show the slide like this. Yeah, so like this is how hippocampal replay is. Okay, if not, I don't think I'll go through the rest. Maybe the rest I will cover it on the next session, because I will go more in depth into reinforcement learning in the next one and how we can use like all these ways of storing and forgetting memories, as well as like how to do this multi-modal key hashing, referencing to help in like reinforcement learning. Of course, this abstraction here is still a work in progress, because like how best to get this abstraction space is an open question. Okay, but I still believe that this abstraction space will form the key to the memories. Like this key to the table here will be formed by the abstraction space. Yeah, so that we can generalize. Okay, yeah, actually that's the end for today. I hope it was interesting. Yeah, you have anything
that's
to
really
ask?
interesting.
Yeah. Or you have any experiences you want to share? Like, I mean, like, how can we best model this memory? Yeah, that's a very interesting thing. Yeah.
But it's like, are you trying to combine the memory component with attention mechanism?
The retrieval part, yes. To retrieve the memory, you use an attention mechanism.
How would you do that? Oh.
Using this kind of like cosine similarity, and then doing like some form of match, and then get either the average value or like the most common value, like if you were to do voting.
But you also need to learn the QKs and the Vs, right?
You will need to learn. I mean, what's the Q and the K? Is it? The Q is the query. So the query will be your current stimulus, what you see right now in the abstraction space. These are the stimulus in your abstraction space. So you don't.
And then but then the key is abstraction.
The key is also an abstraction space, but it's already stored in memory. So the key value is like your episodic and semantic memory. It's already stored in your memory already. So all this thing here maybe is stored. It's either stored in the hippocampus or the cortex, where you like can reference it. Yeah, so it's already stored in your memory. You are just trying to refer back to your memory in order to get something similar in the past in order to use it. Yeah. I mean, it'll be clearer if we go through the reinforcement learning one, but I think I want to keep like 1 to 2 hours for that. It's quite a complex mechanism. That I mean, you can just look at the slides right now. So like this is the like how to model MDP of the world, which means we don't model anymore. We use the key value pair. Yeah, so this is just like a teaser, okay? Because I think I will need some time to go through in detail. I don't want to rush this. This one, I quite like this idea. I came out with it yesterday or 2 days ago. Yeah. Okay.
Yeah, you worked on quite a bit on this
Yeah.
topic.
Then this is reward and pain. How to use pain to prevent your agent from dying. Yeah. So this is another thing that memory can help with. Yeah, like what I said about the snake earlier. The snake, you want to go there. Like you remember a snake at this area, you may not want to go that area anymore because you don't want to get an encounter with the snake. So yeah, this one, these few slides, we'll arrange another date. Yeah, I like to actually go through in detail the ideas there because this is an exciting area, I feel. No one really has done something like this, but this has huge potential, I feel. Okay, if there's nothing else, I'll just like stop the recording already. Okay, thanks.
Yeah, thank you. It's really